Hi, everyone. So this week, you guys are working on the graphs homework. So we'll problems from the graph assignment and some other problems as well. We can with this. And then we can do it. Oh, how am I doing? Can you hear me well, James?
Yeah, now I can, but you cut out there for a bit.
Okay, I just plugged in my Ethernet cable. So, okay, did you hear me say we're working on problem 3? So that's what we're doing. Okay, here's problem 3. So let G be a simple and connected graph which contains one and only one cycle. Prove that the number of nodes in G is equal to the number of edges in G. And you can see the hints there. So take a couple minutes to think about that, and then we'll do that one. All right. Does anyone would like to share their approach for this problem? Or just how you got started?
I got started by kind of just drawing out a little picture of what what this kind of graph would look like. You know, being like I drew it as like a circle or whatever, and I don't know. It makes sense like logically to me, but I don't know how to like prove it. You know what I mean? Using the way that you probably want.
Okay, so a picture is a great way to generate some intuition about how to move towards a proof. So let's start with a picture. You mentioned a circle, and so what we're told is that the graph has exactly one cycle. So a circle is definitely a part of, well, a circle or a cycle is a part of the graph. So this is just one example of a graph that contains one and only one cycle. And we want to show that it has the same number of nodes as it does edges. So let's just say it has m edges. And one of the things that we know is that in trees, if we have a tree, then we know how to find the number of vertices as long as we know the number of edges. So we want to try to use that. So what we're going to try to do is remove an edge, and from that we're going to end up with a tree. And when we have a tree, hopefully we'll know the number of edges. And if we know the number of edges in the tree, then we'll be able to know the number of vertices in the tree. And then we'll add back the edge to our graph, and the number of vertices won't change. So in particular, we're going to remove, so let's say we have a graph G, and let's say that it has m edges. So m edges in G. And now we're going to remove E, an edge that is in the cycle. So we know G has a cycle. So we're going to remove the edge E from the cycle. That produces, so in our picture, what that looks like is removing, let's say we just remove this edge. That produces a new graph G prime. G prime does not have the cycle that it originally had. So, and now there are no cycles in G prime. So, because we got rid of the cycle. But now we're going to use this other fact. So the assumption here is that G is simple and connected, and it contained one and only one cycle. So we removed an edge from the cycle, producing G prime. But our graph G was, it was originally connected, and we removed an edge from the cycle, meaning there is no longer a cycle. And what we get out of this is a G prime, which is also connected. So just to repeat, our assumption about G is that it's simple and connected and contains one and only one cycle. And we just removed an edge from that cycle. And so by this one, since G was connected, the resulting graph, which is G prime, is still connected. And from this picture, we can see why that makes sense. We removed the edge from the cycle, but you can still get from this vertex to any other vertex in the graph. All of the vertices that were connected before removing the edge are still connected, which is all of the vertices in the graph, because the graph was connected. So, all right. So then we have to notice that this is connected, but now we remove the cycle. And so there are no cycles. And so we have a connected acyclic graph. And a connected acyclic graph is a tree. So that means that G prime is a tree. G prime is a tree. So, and there were m edges in G. So G prime is a tree, and the number of edges that it has is one less than the number of edges in G, because we just removed an edge from G. So it's a tree, and it has m minus 1 edges. And so now we're going to use this fact. It's a tree, and it has m minus 1 edges, and therefore the number of vertices is 1 plus the number of edges. And so this means that G prime has m vertices. Okay, and then we notice that to finish the proof, we notice that, well, G prime and G have the same number of vertices. That's because all we did to get G prime from G was we removed an edge. So we didn't touch the vertices. So therefore, G prime has m vertices, therefore G has m vertices, and G had m edges. So G and m have the same number of it has m edges and it has m vertices. It has the same number of edges and vertices, and we're done. That's the idea. When you write it up for yourself, it'll be good to write it up in a more organized way than this. The writing is just giving you an idea of what you need to do, and I hope that from this you have an idea of what you should write down. But you want to be more precise than the scribble that's on the board. Are there any questions about the strategy or like the arguments that went into this? Or if anyone is just completely confused and wants to hear it again, please let me know. All right. There's only 6 of us here, so just shout out if you want to, explain the problem yourself and you're tired of hearing me talk, then that's fine too. Somebody wants to do one of these problems, that would work too. So I'll just assume that people are comfortable with this one, and we will move on to another problem. This one, we'll just do this one, number 4. G is a graph which contains a closed walk of odd length. Use induction on the number of edges in the closed walk to prove that G contains a closed cycle of odd length. And then it gives a hint, which we'll use. So go ahead and think about this one a little bit. All right. So does anyone, it says to use induction, so we should have some kind of a predicate to start with. So let's just start out by writing out our predicates. Does anyone have in mind what they would write down as their predicate? This is just the first step in doing an inductive proof. We need to write down our predicate. All right, well, it says that the graph G contains a closed walk of odd length. We want to show that G must contain a closed cycle of odd length. So we can let P of n be the statement that if G contains a closed walk of odd length, well, of length, actually of length 2n minus 1, then G contains a closed cycle of odd length. Okay, now let me try to make that more visible. Okay, so that's our predicate. If G contains a closed walk of length 2n minus 1, then G contains a closed cycle of odd length. And we're going to prove that for every natural number. So why length 2n minus 1 and not length n? Because the statement is that G is a graph which contains a closed walk of odd length. So that's going to be not just an arbitrary natural number, but it's going to be of the form 2n minus 1. Okay, so in an inductive proof, well, we know the recipe. We're going to start off with a base case. So let's do our base case. So we'll write that out over here. So P of 1. So let's prove P of 1. We're going to prove P of 1. So how do we do that? The statement is that if G contains a closed walk of length 2 times 1 minus 1, so a closed walk of length 1, then G contains a closed cycle of odd length. So does anyone have in mind how to prove P of 1? Okay. So G is a graph and it has a closed walk of length 1. So that just means that first of all, it's closed. So what that means is that the start and end point of the walk are the same. So there's an edge that connects V to V, and that's the walk. So because it has one edge and it connects, it's closed. So it starts and ends with the same vertex. So what it means to have a closed walk of length 1 is just it goes from V to itself. That's a self loop. It's a self loop. So we conclude, well, that's a cycle. It's a cycle of length 1. G has a cycle of length 1. Okay, and that's odd length, so done. Okay. So, if you were being more really rigorous, you would say, okay, so the walk, so there exists a vertex v, and the such that the walk is v to v. This is a self loop. Conclude G has a cycle of length 1. Are there any questions about P of 1? All right, let's do the inductive step. So I'm going to try to do this with another text box. So let's suppose, so we're going to prove, now our goal is to prove that P of n imply, actually, okay, so for this one, sure, usually when we do an inductive proof, we'll just try to show that P of n implies P of n plus 1. And sometimes we realize while we're doing the proof that later on we might need to add in that we need to assume P of 1, P of 2, through P of n, which is valid in the inductive framework. But, originally, if you started off the problem, you might just think, oh, I'm just going to try to show that P of n implies P of n plus 1. And while you were trying to do the proof, you might realize, oh, actually, I need to assume P1 through Pn minus 1 as well. So we'll see why we need to assume P of 1 through P of n minus 1 in addition to P of n while we're doing the proof. So this is what we're trying to prove. So to do that, we are going to so assume, we assume all of these things, P of 1 through P of n minus 1, or P of n. That's P of n. Okay. Now we consider, so in order to show P of n plus 1, we consider G, our graph contains, or suppose is a good word to use here. Suppose G contains a closed walk of length. Okay, so we are trying to prove Pn plus 1. So we're going to assume it contains a walk of length 2 times n plus 1 minus 1, because we are trying to prove Pn plus 1. All right. So then if we just simplify that, that's 2n plus 1. All right. Okay. So now we want to show that G contains a closed cycle of odd length. All right. So now we reference the hint. The hint says that we should consider 2 cases. 1, the closed walk contains no repeated vertex, except for the starting vertex. And 2, the closed walk contains a repeated vertex. So let's do case 1 first. That'll be the easiest case. Okay, so case 1. The walk, I'm just going to call the walk W. Let's just call it W. This is a closed walk. So W is our closed walk. I'm not going to write that down, but if you were writing out the proof, you might want to say, okay, let W be the closed walk of, let's just say that up here. W is a closed walk of length. I'm not sure how to go back to a text box. So, oh boy. Okay, all right, so W is a closed walk. I'm just trying to get a text box again. Okay, there, I got back to the text box I was in, I think. Okay, oh, all right. I'm gonna go to the drawing board. We made it pretty far with that. Okay, so case 1, I'm just gonna write it out here, is that there's no repeated vertex in the only repeated vertex is the last vertex. Okay, and what we want to show is that G contains a closed cycle of odd length. So let's see, what does that look like? It looks like we have some vertex V, and then we have just our walk, and there are no repeated vertices in that walk. So there's an edge here, and then there's another vertex V1, and then there's another edge, and then there's a vertex V2, and none of these vertices are the same right now. We end up having, like a V, what is this? This would be V2N. That's what it would be, V2N, I think, or V2, something like that. That doesn't really matter. It has some length. There's a certain number of vertices in here, but we know that we don't have a repeated vertex. That's what's important. So what we want to show is that there exists a closed cycle of length 2n plus 1. Or a closed cycle of odd length, and 2n plus 1 is odd, so that would be sufficient. And we know that the total number of edges in this, let's just call this VK. The number of vertices here is we're not repeating the vertices. We'll specify K later. That doesn't actually matter for the proof. So what does matter is showing that because we don't have a repeated vertex, that this is a odd length cycle. And we already know that the length of this cycle, or the number of edges that are in this walk, the number of edges in this walk is 2n plus 1, which happens to be odd. So maybe this is a cycle itself. And so let's try to prove that it is. And the reason is because of this. All we have to show, we already know there's not any repeated vertices except the first and the last. So this is VK. It doesn't really matter how many are in there. Then we have edges A to B, let's say that we had edges A to B and B to C. What we're told is that, actually, let me make this a D. What we're told is that there are no common vertices in this walk, and what that means is that there can't be any repeated edges either, because if there was a repeated edge, then it would have to share the same vertices. So let's say that A and B and D to C, those are two repeated edges. What that means is that D is equal to A and C is equal to B, because it's a repeated edge. But what that would mean is that, of course, now we have repeated vertices. So that means that there are no repeated vertices, there are no repeated edges in this thing. And so in this walk, there are no repeated edges. We were already told there were no repeated vertices, and this is closed, and so therefore it's a cycle, and it has odd length. So we've just found an odd length cycle in our graph G. Does that make sense? If not, you should just say it doesn't make sense, and then James or myself can re-explain or make it more clear.
Looks like someone in chat said that they think it makes sense.
Oh, okay. I didn't see that. All right. Okay, so I'm going to erase this case because unfortunately we don't have any space. So that's fine. Then let's do this case. So that was the easy case. Now let's do the more difficult case here. So again, the main idea where there was that if you have a walk and it doesn't contain any repeated vertices except for the first and the last, then, well, it doesn't contain any repeated edges either, because if you had a repeated edge, you would have to have repeated vertices. So that was the idea. So now let's do the other part. So this is case 2, and that's that there is a repeated vertex. So there's a repeated vertex. It's not the first or last vertex. So there's a repeated V star, let's call it V star, and it's not the first or last. It's not the first and last are repeated because this is closed. It's a closed walk, but we're assuming now that there's some V star in there, and it's happening more than once. So now it might be very useful to draw a picture. So let's do that. So we have our, let's say the initial vertex is V0, and then we've got this closed walk, but we know that it visits V star, and then somehow it visits V star again. And then, so we don't know how many times it visits V star. It may visit V star many times. And so this picture isn't necessarily an accurate depiction of what's going on. It's not a perfect picture, because there could be, many of these loops where it's going back and forth to V star, but it gives kind of a general depiction of what's happening. So basically, if you think of this as the beginning of the walk, then it goes all the way up to here, which would be the first time that V star is visited. And then if we imagine that this is the walk from the first time that V star is visited to the last time that V star is visited, and then this is from the last time that V star is visited back to the starting point. That's what this picture is representing. So the idea is the following. So in here, this piece, that's a walk, and it's a walk. It's a closed walk because it starts at V star and it ends at V star. And this piece here, this squiggly piece, that's also a walk. And it's a closed walk. And it's because it starts at V star and it ends at V star. And these two walks, the union of this dashed walk and this squiggly walk, cover the entire walk. That was the line that started from V0 and ended at V0. So this is giving the intuition. When you write out the proof, you'll want to be a little bit more rigorous. Maybe write out the vertices and edges in the walk, and then write out you saw where you see V star and then ... and you see V star again and then ... you get back to V0. That's another way to express this picture, but this picture just gives the intuition. So there are two walks in here. We have two closed walk. Dash, dash, dash is a closed walk, and squiggly, squiggly is a closed walk. And the union of those two closed walks makes up the entire closed walk, the entire closed walk of odd length. So these are two closed walks, and they make up the entire closed walk, the entire line that is the closed walk. And that line, remember that our assumption is that line, it was a closed walk of length 2n+1. So what you want to do now is the dashed line and the squiggly line, they make up the entire walk. They cover the entire walk. The entire walk is of length 2n+1. That means that the sum of the length of this walk and the length of this walk, the sum of the lengths of those two walks is equal to 2n+1. So this is odd. 2n plus 1 is odd. And we have two lengths adding up to 2n plus 1. So from the beginning of the course, we remember that if you have an even and an even, then it has to add to an even. So that means that the lengths of at least one of these two walks is odd. And then what you should think about and write down when you're writing down your actual solution is that, well, first of all, it's clear that these two walks have a length which is no more than 2n plus 1, because these walks partitioned the entire walk. They were sub-walks of this larger walk. So they have length which is less than or equal to 2n plus 1. So, and they also have the sum of their lengths is 2n plus 1, and we already just mentioned that one of these has to be odd length, and their lengths are now smaller than 2n plus 1. So, well, if one of them is odd and its length is smaller than 2n plus 1, well, it can't be 2n because that's even. So its length is some odd number, which is 1 through 2n minus 1. And the inductive hypothesis, okay, so just to summarize, what we have is that one of these two paths, or one of these two closed walks, has a length which is equal to an odd number I in 1, 3, oh no, 1, 3, all the way up through 2n minus 1. So now we use the inductive hypothesis. This is a closed walk of odd length, and so we're using P of I now. So by P of I, so that was up here. This is where we have to assume P1 through Pn and not just Pn, because the length I is not necessarily 2n minus 1. It could be smaller than that. So that's why we have to assume the Pi for I smaller than n. And Pi gives us that this is we have a closed cycle of odd length. So. Okay. Are there any questions about the general strategy? Like if you, for example, if you were confused about just, maybe there was one part of that argument that didn't make sense, or maybe a large part of it didn't make sense or something, it's a good idea, you could ask. And we have an expert here, James, and we're here to help. So okay. Well, I hope it made sense. And just to, if we were in a class writing on a whiteboard, it would be a little bit easier to write down a more formal argument. But with this interface, this is not what you would write down on your homework. I think you probably know that. So, but this is the idea of the proof. So these are all the ideas, and yeah. I hope it was clear. So let's do another one. We'll do one more. Is that okay, James? I could do one from the slide deck if it's not okay to do another one. What do you?
Oh, whatever.
Okay.
I think, yeah, whatever's fine.
All right. Okay. I think that the last one was a little bit more difficult than this one. I just got to figure out how to get rid of everything on the screen. Oh, there we go. Okay. Prove using induction that for a connected graph G with n edges, where n is greater than or equal to 0, then G has a spanning tree. And it gives us a hint. It's 3:35, so take 2 minutes and maybe try to, and when you might not be able to prove the whole thing in 2 minutes, but try to maybe understand what the what the statement is and maybe draw a picture or two to try to start generating some intuition about this problem. All right. So it's proof by induction again. So we're going to want to write down some kind of a predicate. So I'll just do that. So it says, using induction, prove that G has a spanning tree when it's provided G is connected. So, and it says the number of, this should be done for an arbitrary number of, if G has an arbitrary number of edges n. So we're going to make a predicate here. Pn is going to be the statement that if G is connected and has n edges, then where n then G has a spanning tree. Okay, so, and then we're going to prove this. This is for n greater than or equal to 0. N is a natural. It's 0, 1, 2, 3, 4, etc. One of those. So we'll have to do it for our base case. Our base case will be P of 0. Does anyone want to prove P of 0 or have an idea in mind that they think might be right? Yep. That's right, Miles. It's one node, and that's a tree. Yep. So and that's the base case. So it's a tree, and we're done. That's the base case. So the one node on its own, if you just have this one node, it doesn't have the graph doesn't have any edges. We also know it's connected, so we don't have something like this. If let's say that G wasn't connected, then we could be in a situation where we had two vertices and no edges, in which case there is no spanning tree. There's no collection of edges that's going to reach all of the vertices. But Miles observes that this is a connected graph, and it has 0 edges, and that means that it can only contain one vertex, and a vertex by itself is a tree. That vertex by itself is a tree in this graph. So that's the base case. Now the next step, we're going to suppose Pn for some n greater than or equal to 0, and we're going to want to show Pn plus 1. So we're going to take or consider G. We're going to consider a graph G with n plus 1 edges. G n plus 1 edges has n plus 1 edges. All right. And we want to show that G has a spanning tree. That is our goal. So we're given a hint. It says if an edge is removed from a cycle in a connected graph, the resulting graph is also a connected graph. Well, the first thing, we want to use that hint, but our graph may not have a cycle. So maybe we can use that hint if we had a cycle, but if we don't have a cycle, we're not going to be able to use that hint. So we must have to handle the case of not having any cycles differently. And so let's write out a case 1. Case 1 is that G has no cycle. And if that is the case, then G is a connected acyclic graph. And a connected acyclic graph is a tree. So this implies that G is a tree. And if G is a tree, then we're done. Then definitely G contains a spanning tree. The graph itself is a spanning tree. Because the graph is a tree, so the tree that makes up the graph reaches all the vertices in the graph. So the tree is a spanning tree. And so it contains a spanning tree. So the other case, case 2, is that the graph contains a cycle. So now we're going to use the hint. It says here that if we remove an edge from the cycle, which we can do, we have a connected graph G, it contains n plus 1 edges, it has a cycle, we'll remove an edge from the cycle, then the resulting graph is still connected. So so that's what we do. We remove the edge, and now we have a new graph, G prime, which has one less edge, and it has n edges. Well, our inductive hypothesis says that if G is connected and has n edges, then G has a spanning tree. So now our G is our G prime being the graph where we removed the one edge. So G prime has n edges, and by the hint, G prime is connected, and so by the inductive hypothesis Pn, G prime has a spanning tree. So that spanning tree that it spans G prime, well, it also spans G, because G prime and G have the same vertices. And that's because the edge that we removed from G prime, the edge that we removed from G to create G prime, we didn't remove any vertices. All we did is remove an edge. So again, just to summarize case 2, we had a graph G that had n plus 1 edges. We wanted to show that it had a spanning tree. We removed one of the edges in the cycle. Our assumption was that it had a cycle in case 2. We removed an edge where it had a cycle. That created a new graph G prime that had n edges instead of n plus 1. We used the hint, and that told us that this graph is still connected. So G prime is connected, and it has n edges. We used the inductive hypothesis then, which says that G prime has a spanning tree. And then we argued that, well, G prime and G have the same vertices. So a spanning tree for G prime is a tree that covers all the vertices in G, because G and G prime have the same vertices, and so it's a spanning tree for G. So that completes the inductive hypothesis. And we're out of time, so at 2 p.m., James is conducting a quiz review for next week, so I encourage you to attend if you have the opportunity. Other than that, we're done, so have a great day.